Hello guys, welcome to Investing with JYK, and today we'll talk about mobile CPUs. This may or may not interest you, but it's kind of important for understanding certain businesses like phone makers and mobile CPU makers such as Qualcomm, Apple, Samsung, and probably Huawei, or even MediaTek if you're aware of them. So almost all mobile phones use CPUs that utilize the ARM architecture. So ARM has multiple versions of their architecture. For example, here is a list of ARM v7 application cores. And then here is a list of ARM v8 cores. The v8 ones are the current high performance instruction set. And so you can see a bunch of them made a bunch of cores. And you can see at the top of the thing, it's always ARM something. So now ARM is the company that created the instruction set, ARM, that also designs CPUs called ARM. So these are ARM Cortex A32, whatever. So they design these CPUs, but they don't make them. The way ARM makes money is three ways. One, it licenses the instruction set. So if you build a CPU that conforms to the ARM instruction set, you have to pay them. The fee is typically very minimal, on the order of dollars or even less for older instruction sets. And the second thing is they can license you the design of their CPUs as a whole, and you can put their CPUs together, and then put in things like a GPU, which ARM also will sell you a design for. They sell these Mali CPUs, and they would sell you, so they will sell you those things, and you can put up DSPs or modems on the same silicon to make a SoC, system on chip. And these are the things that are typically put into phone. These SoCs, for example, Snapdragon is an SoC. It would have a DSP, a digital signal processor, a modem, and it would have a CPU, and it would have a GPU. Right, so that's an SoC, and that's typically the unit that these phone manufacturers buy. All right, so that's the second way ARM makes their money. The third way is it will license you a design, but also grant you the ability to modify them in however way you want. So you can see, if you just license the design in its entirety, it's the lowest technical challenge. There's still a lot of challenges in putting them together, and finding the proper components, the GPUs and DSPs to go with them. But that is technically the easiest way. So you can see like MediaTek, for example. MediaTek, Huawei, which has their Kirin thing, cores, Kirin cores, and Kirin SoCs, I think, and some others. They basically just license the cores, so they cannot design, they cannot even modify the design. They don't have the technical ability to do it. And then the ones that license the cores and modify them is, for example, Qualcomm being the most significant player here. And then there are, and I think Samsung does it too. And then there are complete designs. So basically, Apple only licenses its instruction set, and Apple designs its ARM cores on its own. Obviously, that's obviously the most difficult one, but then that also affords you the biggest potential for performance advantages. So Qualcomm used to build its own cores completely. So that happened with ARM v7, and the Qualcomm Crate is a complete new microarchitecture. Has almost nothing, very few things in common. So it's ground up built by Qualcomm, and you can see it's ground up because if you compare it against the ARM designs, right, you can see the decode width is different, execution ports is different, and the pipeline length is, well, same as A9 and A12, but not A15. And it has out of order execution, unlike a lot of the older ARM cores. And it does the let's see, it doesn't support big little, because that's something new that ARM added late in the life cycle of this instruction set version. And you can see it even has an L0 cache, which is, all the cache sizes are different, and yeah, you can see everything is different. So this is really really a full custom design. And the other thing is, if you compare the speed per core in terms of Drystone million instructions per second per megahertz, Crate was 3.3, 3.5, and this stuff was better than everything before A15. Right? You have A17 that was arguably better at 4.0. So this number is very important. We can get into that slightly later. Apple at that time did not have much advantage compared to Qualcomm. And then later in the V8 timeline, you can see that Apple went completely crazy with their design. For example, if you look at decode, Vortex, the Apple high performance core, has 7 wide decode. And if you look at the pipeline depth, it is not the same as any of the ARM designs at 16. Out of order execution, obviously it supports it, but there's not much more information about it. And then if you look at execution ports, this thing has 9 execution ports, which is not the same as any of the ARM designs. So you can see this is a really completely new design. Same as here. Cache, L1 cache, is bigger than every single other design you can ever see. Same as the L2 cache. Right? So first we now know that this is a full redesign. But now if you go to Qualcomm, this one doesn't actually say much here, but if you look at their own thing, they said something about so if you look at, what the hell? Anantech, which is a very good tech website if you care about tech, that is. What is wrong with this stuff? Why doesn't it like me? Okay. You can see both all these cryo, even the 485s were A76 derivatives. So basically they were based on A76. what they do have different is they have slightly bigger caches. Essentially, it's a A76 with bigger caches, but Apple, on the other hand, has a full redesign, right? So what does that buy in terms of performance? Now let's go to here. This is basically a notebook check, but it has a bunch of CPUs and a bunch of benchmark results, so you can compare them. If you look at the single core performance, Apple is essentially better than everything else. It's better than Cryo whatever. It's better than your Samsung Exynos. Better than everything. Why? Well, especially on the single core performance, because they built these CPUs to, if you just go to this one, to extract as much instruction level parallelism as possible. And what that results is very high single thread performance. And for example, they have a 7-wide decode compared to 4-wide. That means for every clock cycle, each second will give you like 2.5 billion cycles, because that's 2.5 gigahertz or whatever these things run at. So for every clock cycle, you can potentially decode 7 more new instructions, and they will be they actually pull them together, and then you later decide which one you can actually run. It's quite involved, so that's actually where this out of order execution stuff comes in. You have a bunch of instructions that's pulled together, and then you have to decide which ones you can execute, because there are dependencies, right? You can imagine if I want to add x equals y plus z. Now, in order to compute x, you have to know the value of y and z, and maybe y and z is computed one instruction before, so you cannot execute instruction x equals y plus z until you have obtained the value of y and z. So these are data dependencies, and you have to resolve these. So you cannot overcome data dependencies. You can overcome a lot of other things like control dependency by this thing called a branch prediction. We won't get too much into that. It's very involved already. And the other thing is the pipelining. This thing has 16 stages of pipelines instead of the normal 13, 11, or 15. And what does that buy us? Now, imagine if you have a car assembly line, you can split into multiple stations, right? On one extreme, you have a single station, which means a single guy works on the entire car. On the other extreme is you have, say, 1 million stations, and everybody just do one twist on a knob. Now, both of these are inefficient. On the one hand, you got a single station. There's no specialization, so he probably can't get much faster. He cannot perform at his peak potential. Same with CPUs. The hardware can't do everything simultaneously, so you have to the thing becomes very slow. On the other extreme, if you have 1 million stations, it takes a lot more time for the car to travel between station to stations instead of being worked on these stations, because now if each station is 5 meters, now you have a 5 million meter long assembly line, which is extremely wasteful. And there is also a limit on how fast you can move these cars on these assembly lines. Same with CPUs. If you have too much pipelining, on one hand, you will get diminishing returns because at every end of the clock cycle, you need to be able to save the result of that operation. And that time is though small, that overhead is though small, is constant. So if you split into a million stages, obviously your essentially the entire time between each clock cycle is going to be taken up by these saving things. So that doesn't work. On the other hand, you also have issues with more and more control dependencies and data dependencies, and there's only so many instructions you can run that are not dependent on each other. So you also get a diminishing return there. But higher pipelining typically enables you to run the CPU at higher clock speeds. So and then you can see here the execution ports. This thing can execute 9 instructions in one go potentially, which is quite crazy. I think there was a thing I was looking at that surprised me a lot. Was it this? Oh yes, I think it's here. So these are ARM designs, right? This is a Samsung design, and this is Apple design. So it can do 6 adds in one cycle, and it takes 1 cycle to complete the adds. That's pretty simple. It does 2 multiplies in 1 cycle instead of 1 for the ARM designs. And you can see this theme continues. You got the 2 multiplies, 64-bit number of multiplications in 1 cycle, and these only do 1. And integer division, it's slightly slow. And here is very important. I actually got bitten by this when I was coding once. I was using a division to compute the hash number, and that just killed my performance. That was crazy. Until I figured out, oh, damn, division really killed my performance, and I changed it into a multiplication. But that's another story. And same here, move is better than the ARM ones, and shift is better, and almost everything is better than the ARM design. Well, not necessarily better, but faster. It has more potential to execute more instructions simultaneously. It comes at a cost of larger chip size. It comes at a cost of power consumption, but that is what you end up getting. And this continues for almost every single operation. And the result is, for example, if you look at, let me see if we can get it. Let's do an Optane and remove this stuff. Okay, I'll keep this on. Remove these. These are old stuff. I don't really care about these. Okay. Right, Optane is, Octane is the JavaScript test. And that's very important. Why is that? Okay, let's put the Jetstream as well. These are JavaScript tests, because a lot of times your mobile phone is essentially just running JavaScript, which is your web browser. Anytime you interact with HTML5, you're using JavaScript. And a lot of apps nowadays are also written with the React Native, which is also run, where the business logic is also run in JavaScript. And you can see Apple is just dominating, especially in the JavaScript side. It's just dominating everything, right? It's quite crazy. It dominates absolutely everything. Why is that? Well, because JavaScript is single-threaded. So that means you can only use at most 1 core at a time. You can not split the task among the other cores. So if you look at the configurations, let's just compare the new ones. Apple uses two of these high performance Vortex cores and 4 Tempest. These are the power saving cores. So for 6 in total. But really, when you're running JavaScript, only one of these Vortex cores are active, right? And then they are, as we discussed, super powerful. You can also see the cache is insane. So 128 plus 128 compared to the ARM design at 64, so you have double the cache size. The L2 cache size is even crazier. You got 8 megabytes compared to these ARM designs at half a megabyte. So it really shows in the benchmarks, and the result is that anytime you do anything single-threaded, the Apple phones, iPhones, perform a lot better than most Android phones, because the Android phones just don't have the CPU. Obviously, the advantage goes beyond that because the language of the apps, so the language in which these apps are written are different. In Apple, it's Objective-C, which is compiled basically down to machine code, and the CPU just ingests the machine code. It's very simple. In terms of Android, a lot of times it's bytecode, which means there's one more level of translation. You have to translate the bytecode into machine code and then run it. And there's some tricks you can do to make that faster, but the cost is there nonetheless. Right, so, and then if you think what is single-threaded, UI is single-threaded. So when you are swiping, that's single-threaded. If you do this, it's single-threaded. And JavaScript is single-threaded. So a lot of the things you do on a phone is single-threaded. So what that means is if you have 8 cores, most of the time you will have one core working really hard, the other 7 cores staring at it. In order for that to not happen, you need a programmer to be very careful about how to split the task, and then you have to be very conscious about how you split. It's very difficult to code multi-threaded things, right? Any programmer can tell you that. If they can avoid it, they won't write it in multiple threads because it's not natural. A human does not think in 3 or 4, or in this case 8 streams of consciousness. That doesn't happen. We have a single thread of thought, and then we can switch between thoughts, and then we have to do a bit of a context switch to pick up where we left off before. So same with essentially the most of the mobile apps. They can't take advantage of a lot of these cores. This is different for desktops, because on desktops you have 20 apps open, or 20 windows open in my case, or something like that. On a phone, you can't really do that because you want to conserve power. So once your app goes on the background or your page goes on the background, it basically gets suspended or sometimes get killed. So you really can't take too much advantage on these numerous cores. So a lot of times they'll say, oh, we have octa-core or I don't even know how to say 10 cores, but 10 cores or 12 cores. It's pointless. It's not a server. On a server, it's very simple because for a programmer, because it's very natural, because you have 10 clients connected to you. You get 10 cores, and then you just send one core off to each one of them. These cores don't even need to talk to each other because they just serve a single client. Obviously, it's slightly more sophisticated than that, but the gist is that on a phone, you don't have 10 clients connected to you, right? You don't have 10 apps simultaneously running. So I would say for phone, if you want buttery smooth experience on a phone, good user experience on a phone depends a lot more on single thread performance than on the number of cores. And here are the numbers to prove it. And if you talk to any iPhone user, they would always say, almost all of them would say, I choose an iPhone because it doesn't lag. Why doesn't it lag? Because it has one of the reasons, because I have a better CPU. All right, haven't talked about all these random crap. what does it have anything to do with investing? So a couple of observations. So Qualcomm has, I would say, deteriorated from doing complete new designs to just a modification on the ARM design. And it really started happening right after Crate. Crate was pretty good. And after Crate was Snapdragon 810. Right, Snapdragon 810 essentially just put a bunch of A73, I think, cores in there, and it overheated. As the first time Qualcomm did that, and Snapdragon 810 was no better than any other, actually worse than any other SoCs that use the same ARM cores. And then after that, they went to these cryo cores, which are basically modifications on the ARM designs as well. So that's one thing. So I would say the brand name Snapdragon probably would deteriorate a little bit. Yeah, I mean, like, if you look at their single-threaded performance, I think I was looking at one. It basically is just no longer standing out compared to everybody else. I think it was a Geekbench or something. Oops. Bench. Nope. Geekbench? Nope. Let's see. If I can't find it, I'm gonna give up. All right, here we go. Yeah, Geekbench. Look at this number. 64-bit single core, single threaded, 3.5K. And where is that? That's the same as Apple 10 Fusion from A10, which is from, I don't know, long time ago. Right, we're now at 12, so maybe you were like 2 years ago or something. And slightly better than Killing, because they are actually modified ARM cores. They are modified. They're not just that. And you can see it's basically on par with this Exynos M3 thing. I'm not actually sure what this weird color is, but yeah. So it doesn't stand out anymore. It's just another one of those. And the other thing is they kind of realized that. So essentially, they also did something with more than just big little. So they now have this prime core stuff. Yeah, so they now have a single prime core that goes up to 2.8 gigahertz. So they basically boost up the clock frequency. But the normal Cryo 485s are 2.4 gigahertz. So they have like one that goes at 400 megahertz higher. Again, as I said, most of the workloads are single-threaded, so you really want something that's really fast at doing a single thing, a single control flow, and kind of compensating for a little bit for what they were missing compared to I mean, before, when you say Snapdragon, it was just leagues ahead of everybody else. They're just better. Now, I mean, I don't really know if they're that much better than the competitor anymore. But so that's on Qualcomm. Doesn't mean I'm bearish on Qualcomm, the company. I just, in terms of product, I think they are deteriorating. In terms of Apple, I like what they do. So Apple has a big enough market share and big enough revenue share and profit share that they really want to maintain this premium device thing. Now, a lot of say, oh, Apple's stopped innovating. But if you think about it, they really hit the nail on the head. They knew the important thing about mobile performance is single thread performance. So they built these ginormous cores that are really powerful. It's very expensive to develop a CPU, but they did it. They did it from ground up even. not only that, they did the GPU in-house as well. So their GPU is actually much better than everybody else's. I don't have the numbers, but trust me, their GPU is much better than everybody else's on the phone. Their CPU is much better than everybody else's on the phone. Now you have the hardware advantages that nobody can even match at the moment. And then the iOS has a bunch of things that tries to ensure user experience, and it shows. In the end, an Android phone is just laggier. For example, I was writing some random app on React Native. On iPhone 6, it's fine. On a Pixel, it lags. I mean, the list wasn't even that complex. It's somewhat complex. It's not even that complex, and yet on a Pixel, it lags. So yeah, I mean, there's also software issues within that, right? But hardware is one thing, a very important contributor. So I feel like this is the one thing that, when you think about the moat, right? When Buffett talks about the moat, Apple is trying to strengthen its moat from almost every single layer. Their vertical integration is not really focused on margins. It's really focused on user experience. They made their own CPU to have the best single-threaded performance. They made their GPU to have the best 3D performance. And they made their own operating system with a bunch of tweaks. They even inverted a lot of these touch control. So the touch control sequence is actually different on an iPhone than an Android. The logic is all different, just because they want to make sure that the experience is buttery smooth. So they tried it from all angles, and it only works because it's them. So they really built up on it. They did not start off with their own CPU or GPU or a lot of the other things that they currently now have in-house. They started with just an iOS, and they bought everything third party. But once they got the profit in, what did they do? They say, okay, how do I make the experience better? They invested in some technology that keeps their lead. Now you can argue that iPhone is less innovative every time. On the wow factor, yeah. So that's something that's hard to do. How do you wow all the consumers when the whole market is pretty mature? But they try, and then they are succeeding in a lot of angles. And I'm an Android user. I like Android a lot more than I like iPhone. But I have to say that in terms of pure user experience, Android just cannot beat iPhone. It's true. And so you keep on building your moat, keep on widening it, at least in some areas. In some cases, it's getting narrower because in terms of wow factors, iPhone is no longer that cool. But that's that, and that's all from me today. And hopefully I haven't bored you to death. See you next time.